Okay, there it is. Okay. In 15.1 and 15.2, the limits of integration have been either we started over a nice rectangle where you went from number to number, number to number. All right, in 15.2, limits of integration go over more unusual shapes, but they were still pretty straightforward, triangles, things like that. All right, there are times when what you are integrating over is more circular in nature, in which case you would want to switch to something called polar coordinates, well, which we already. So if you're integrating over a circle, you could divide this and you could solve this for y squared and go from the square root of whatever to the square root of whatever, but it makes it really complicated. In this one, you could do a square root here, you could do a square root here, but it's just too complicated. It is easier if you go back and switch everything to polar coordinates. Now, the trick to doing polar coordinates, let me kind of give you what we're doing. All right, if you've got, say, polar curves here, this is R is equal to A. This is R equal to B. You're integrating over this region here. And you want to go between an angle here, which is alpha, and an angle here, which is beta. Now remember, polar coordinates are r's and thetas. You go out r on this line, and theta is the angle right here. Okay, so you have r's and thetas. If you want to integrate a function over a region D, but your D is like this, more circular in nature, then you can change it to polar coordinates. Whoops. All right, and if you'll remember polar coordinates, the definition x was r cosine theta, y is r sine theta. So what else did we have? We had x squared plus y squared is equal to r squared, and we had the tangent of theta was y over x. Those were our polar coordinate definitions that we had way back in, I guess, chapter 10 or whatever. So if you're going to switch this integral from x's and y's to polar coordinates, then you're going to change your limits of integration to, I can put alpha here to beta. The inner limits would be from a to b, that's my r's. You change your function from x's and y's to a function of r cosine theta, r sine theta. You have to put an extra r in the problem, and then you do dr d theta. And I'm assuming here that theta is ranging from alpha to beta, and r is ranging from a to b. This extra r is necessary when you change from rectangular to polar. And don't ask me why, it's just because. So I'm sure there, no, I'm not proving it. I'm going to tell you to look at your book. No, look at your book to prove it. Look at your book. Y'all would be asleep by the time, exactly, I know you are. You'd be asleep by the time I got my picture drawn. All right, so suppose, let's look at, let me just show you how this is done. Let me look at a problem number 7. Double integral over the region D of x squared y dA, where D is the top half of a disk with the center at the origin and a radius of 5. All right. When you're graphing these regions, just like we did in 15.2, you need to plot your region so you'll know what you're doing. All right, so if you plot your region, you're doing the top half of a circle. The center is at the origin. It has a radius of 5. And you are integrating over that area right there. Now, if I weren't going to change this to polar coordinates, I could find the equation of that circle in x's and y's, and I could do it all that way. But it is too easy to do it the other way. Now, if I'm going to change everything to polar coordinates, I need to know what my r is, and I need to know what my thetas are going to be. All right, first of all, let's tackle theta. All right, it is starting at 0, and we always go like this. This is going from 0 to pi, because you're doing half of that circle. And your r's. The r is from here to that line right there, but that's the line r is equal to 5. The radius is 5, so you're going from 0 to 5. So when you set up this integral, it doesn't matter which limit of integration you put on the outside because they're both constants. You could do 0 to pi on the outside, 0 to 5 on the inside. Now, you cannot leave the x squared and the y in here. These have got to be changed to polar coordinates. But you know x is r cosine theta, so x squared, r cosine theta squared, times y, which is r sine theta, times an extra r, times dr d theta. And excuse me, that is what you put in to integrate. And if you want to simplify it a little bit before you started integrating, it would be 2, 3, 4. That would be r to the 4th, cosine squared theta, sine theta, dr d theta. And you start from the inside and work out with your integration. Okay, do we actually need to integrate this, or can I just, you're fine to put it in your calculators, just make sure you do it correctly. What mode do you need to be in with your calculators? Radian mode, even though you might have it in there for physics, you might have it in degree mode. Switch your mode to radian mode here, okay? Okay, what else do I need to look at? Let's look at let's look at number 19. All right, number 19, use polar coordinates to find the volume of the Gibbons solid. It is under the paraboloid z equals to x squared plus y squared, and above the disk x squared plus y squared is less than or equal to 25. They want the volume, which means we're going to do a double region over the region, a double integral over the region D of x squared plus y squared dA. That's what it is in rectangular. Okay, that's to get your volume. All right, to get to polar coordinates, or to get your limits of integration. This is the picture in the xy plane. And that just so happens that is a circle with a radius of 5. And you're integrating over that entire thing. That's what's down here in the xy plane. this x squared plus y squared is the function that's up here somewhere. Okay, function is up here somewhere. This is your, in the xy plane. In the xy plane, I'm changing this to polar coordinates. So theta this time, you're going all the way, you want the whole circle. So you're going from 0 to 2 pi. And your r is going again from 0 to 5. And your limits of integration, 0 to 2 pi, 0 to 5. X squared plus y squared, it's got to be in polar coordinates, r squared, times your extra r, and this is dr, this is d theta. So that is what you integrate. Question about this?
It doesn't matter which way you do it if you normally do it.
It does not matter at all. I'm doing it this way simply because that's the way they gave the definition. They put the thetas on the outside and the r's on the inside, but it does not matter at this point. Now, it's going to matter in a minute, of course, when these are not just numbers. If this is a function and this is a function, then these are going to be functions of theta, and these are going to have to be on the inside. But I'll show you that in just a second, okay? Number 8, double integral over a region R of 2x minus y dA, where R is the region in the first quadrant, enclosed by the circle x squared plus y squared equals to 4, the lines x equals 0, and the line y equals to x. All right, so we've got to draw this stuff. You've got to draw your region R. Or you're in the first quadrant. Okay, the first quadrant. X squared plus y squared is equal to 4. That's a circle with a radius of 2. So I'm going to draw at least that part in the first quadrant. The line x equal to 0, that is your y-axis. And the line y is equal to x, which is that line right there. Now, which part of this thing am I integrating over? I need to know which part to shade. Do I shade this upper part or do I shade this lower part? The upper part, because it's bounded by x equals 0 and this line, this is the part that I need. Now, in terms of theta, this line y is equal to x splits this into two pieces, so this is the angle pi over 4. This is the angle pi over 2. So your thetas are going from pi over 4 to pi over 2. Your r is going from 0. This is the circle with a radius of 2. So your r's are going from 0 to 2. So when you set up your limits of integration, you still just have constants, so it doesn't matter, but I would just do pi over 4 to pi over 2. R's are from 0 to 2. The 2x, that's going to be 2r cosine theta, minus y, which is r sine theta, times your extra r, then dr, then d theta. And then just integrate that. Okay, questions? All right, I'm going to do one more. I'm going to change it so that All right, suppose this is angle alpha, and this one is angle beta. You have a function out here, and you have a function out here, and you're integrating over here. This is h sub 1 of theta. This line would be h sub 2 of theta. These are functions of theta, so they have to be on the inside. So your r's are going from h sub 1 of theta to h sub 2 of theta. Your thetas are still going from alpha to beta. And when you integrate, alpha and beta have to go on the outside. The functions of theta have to go on the inside. And then you do your r, dr, d theta. And your function is there in terms of r and theta. Okay. This is especially used when you want to find an area. Now those other, we were finding volume. We had a function here on top, have a function over here, and then you've got this here, you're finding a volume. You can use a double integral to find an area of the surface. If you're looking for an area, then you integrate 1 dA. That is going to be the function if you're asked to find an area. And that will give you the area in 2 dimensions of any shape you're looking for. So you could do an area as a double integral also. I'm just going to show you how to do that.
So that would be in polar coordinates, it would just the r.
Pardon?
In polar coordinates, it would just be r, dr, d theta.
No, you still would have, yes, it would just be r. I'm sorry, yeah. You still have your limits of integration, but you just put r. 1 times r, which is r. Yes. Yeah. All right, you do that when you want to do something like number 15. This is going to look awfully familiar. This is one of some of your favorite stuff. This is saying use a double integral. They're telling us to use a double integral to find an area, and they want 1 loop. I had a feeling when I said that.
I actually did really like that.
Did you? Then you'll love this. 1 loop of the rows, r is equal to the cosine of 3 theta. We want the area of 1 loop. No volumes, but just an area. And then let's use a double integral. Okay? So, remember how to graph this creature? Yeah, so let's go over a little bit of it. Alrighty. This 3 affected the period. The period of this graph is 2 pi divided by 3. So at least I've got to get 1 loop. So I need to go all the way out to 2 pi over 3. So half of that would be pi over 3. Half of that is pi over 6. 2 pi over 6. 3 pi over 6, but that would be pi over 2. Cosine theta has an amplitude of 1. I don't have to graph the entire thing. Okay, because they didn't ask for all the roses, all the rose petals. They asked for 1 petal. Now, if you'll remember, at 0, this starts at 1. At pi over 6, it is back down here to 0, so that's at pi over 6. At pi over 6, it switches to negative, and so at pi over 3, I am down here when I should have been up there, and then back when I get to pi over 2, I am back up here. Just going to keep going. I need 1 rose petal. You're looking for an area. You can use symmetry because you're looking for an area. It's a flat surface. So you have a choice on your limits of integration. All right, they want us to use double integral and polar coordinates. So my thetas. If I want to get one complete rose petal, it's that right there, which went from pi over 6 to pi over 2. That is one rose petal. Your R's. Your R is going from 0 to that line right here. 0 to this line. Well, this line is the cosine of 3 theta, because that's what they told me R was. So since I'm looking for the area, I need the integral from pi over 6 to pi over 2. I have 0 to the cosine of 3 theta, 1 times r, dr, d theta. You always add the extra r, even if you're doing an area. That's going to give you the area of that loop. Is there a question?